Hi future scientists, I'm Atom. In this lesson, we will discuss exothermic and endothermic processes, bond energy calculations, energy diagrams, and some practice questions. The law of conservation of energy states that energy is conserved for both physical and chemical changes. In order to understand the role played by energy in both these processes, first let us define what system and surroundings mean. So system is something that we focus on, and surroundings is everything else that is not part of the system. So what is the exothermic process? Methane reacts with oxygen gas to form carbon dioxide and water vapor. Heat energy is released. In this case, energy is released from the system, which is a reaction, to the surroundings, thus increasing the temperature of the immediate surroundings. So the combustion of methane is an exothermic reaction. Fireworks, rusting of iron, freezing of water to ice are some other examples of exothermic processes. Then what is the endothermic process? Melting of ice is an endothermic process since the ice absorbs heat from its immediate surroundings in order to melt. In this case, the system, which is the ice, absorbs energy from the surroundings, and the ice transitions from solid to liquid. Because heat is absorbed from the surroundings, the temperature of the immediate surroundings decreases, making the process of ice melting an endothermic process. Baking bread, photosynthesis, electrolysis of water are some other examples of endothermic processes. Bond energy calculations to determine if a chemical reaction is exothermic or endothermic. Hydrogen and oxygen combine to form water. In any chemical reaction, bonds are broken on the reactant side and bonds are formed on the product side. Since atoms are held together by bonds, energy is absorbed when bonds are broken. Energy is released when bonds are formed, since the electrons move from high to low energy stable states. The energy needed to break 1 mole of a specific bond is called bond energy or bond enthalpy. Enthalpy refers to the energy stored in a system. Change in enthalpy is negative for exothermic processes and positive for endothermic processes. The hydrogen single bond hydrogen has a bond energy of 436 kilojoules per mole. Oxygen double bond oxygen is 498 kilojoules per mole, and oxygen hydrogen single bond is 464 kilojoules per mole. So step 1 in the bond energy calculation is to rewrite the given equation in the form of bonds. So 2H2 plus O2 gives 2H2O can be written as 2 hydrogen single bond hydrogen plus O double bond O gives 2 times 2 O single bond hydrogen, because there are 4 OH bonds in the 2 water molecules. Step 2, calculate the energy absorbed to break the bonds. So that will be 2 times 436 kilojoules for the 2 hydrogen-hydrogen bonds and plus 498 kilojoules for the 1 oxygen double bond oxygen. And that equals 1370 kilojoules per mole of energy. And this energy is absorbed to break these bonds. Step 3 is to calculate the energy released when new bonds are formed. So on the right hand side, we have 2 times 2 times 464, because there are 4 OH bonds, and that is equal to 1856 kilojoules per mole of energy. This much energy is released when the new bonds are formed. Step 4 is to calculate the net energy change or enthalpy change of the system. So the enthalpy change is shown as delta H, and that equals energy absorbed minus energy released. So it will be equal to 1370 kilojoules per mole minus 1856 kilojoules per mole, and that equals negative 486 kilojoules per mole. As you can see, more energy is released than absorbed, so it is an exothermic reaction. Also note that in an exothermic reaction, the delta H is negative. since the enthalpy of the system decreases as some of the energy is transferred to the surroundings. Nitrogen reacts with oxygen to form nitrogen monoxide. The average bond energy for N triple bond N is 946 kilojoules per mole, O double bond O is 498 kilojoules per mole, and N double bond O is 631 kilojoules per mole. So let's rewrite the equation in the form of moles. So that is N triple bond N plus O double bond O gives 2 times the N double bond O. So the energy needed or the energy absorbed to break the bonds will be equal to 946 plus 498. And that equals 1444 kilojoules per mole. Now let's calculate the energy released when new bonds are formed. So that will be equal to 2 times 631, which equals 1262 kilojoules per mole. The net energy change or the enthalpy change of the system equals 1444 kilojoules per mole, which is energy absorbed, minus 1262 kilojoules per mole, which is energy released. And that equals plus 182 kilojoules per mole. More energy is absorbed than released, so it is an endothermic reaction. Also in an endothermic reaction, the delta H is positive since the enthalpy of the system increases since energy is absorbed from the surroundings by the system. Next is energy diagrams. Energy diagrams or potential energy diagrams illustrate the energy changes that occur during a chemical reaction graphically. The potential energy is shown on the y-axis and the progress of the reaction on the x-axis. Let us draw the energy diagram for a firecracker explosion. Firecracker explosion is an exothermic reaction since the system releases energy to the surroundings. The reactants in the firecracker have high potential energy, so we place the reactants high up on the y-axis. This is the starting point of the reaction or the initial energy state of the system or the initial enthalpy state of the system. Transition state or the activated complex is the highest energy point for the reaction. Reactants must overcome an energy barrier for the reaction to happen, and this is the activation energy that reactants need to kickstart the reaction. Activation energy is shown as EA, and that equals the energy difference between the reactants and the transition state, which is the peak of the hill. For the firecracker explosion, the products have a low potential energy since it is just the burnt and charred remnants of the firecracker. This is the ending point of the reaction or the final energy state of the system. The difference in potential energy between the reactants and the products is the net energy released by the system or the change in enthalpy of the system. In an exothermic reaction, the energy of the products is less than the energy of the reactants. Net energy is released by the system, which means the enthalpy of the system goes down and delta H is negative. Let us assign some fictitious values to an exothermic reaction energy diagram. PE of the reactants equals 500 kilojoules per mole. PE of the products equals 50 kilojoules per mole. The transition state peak is at 800 kilojoules per mole, which means the activation energy equals 800 kilojoules per mole minus 500 kilojoules per mole, which equals 300 kilojoules per mole. Change in system enthalpy equals 50 kilojoules per mole minus 500 kilojoules per mole, and that equals negative 450 kilojoules per mole. Since delta H is negative, this is an exothermic reaction. Let us draw the energy diagram for baking a cake. Baking a cake is an endothermic reaction since the system absorbs energy from the surroundings. The reactants in the cake batter have low potential energy, so we place the reactants low on the y-axis. And this is the starting point of the reaction or the initial energy state of the system. Here also the reactants must overcome an energy barrier for the reaction to happen, and that is the activation energy, which equals the energy difference between the reactants and the transition state. For the cake baking, the product, which is the cake, has a high potential energy since it has absorbed energy for about an hour or so and is hot in the oven. This is the ending point of the reaction or the final energy state of the system. The difference in potential energy between the reactants and the products is the net energy absorbed by the system or the change in enthalpy of the system. In an endothermic reaction, net energy is absorbed by the system, which means the enthalpy of the system goes up and delta H is positive. Let us assign some fictitious values to an endothermic reaction energy diagram. P of the reactants is 20 kilojoules per mole, P of the products is 500 kilojoules per mole, the transition state peak is 800 kilojoules per mole, so activation energy equals 800 minus 20, which equals 780 kilojoules per mole. Change in system enthalpy equals 500 minus 20, which equals plus 480 kilojoules per mole. Since delta H is positive, it's an endothermic reaction. Practice questions. 1. In an endothermic reaction, the temperature of the surroundings, blank, while the temperature of the system, blank. In an endothermic reaction, the temperature of the surroundings decreases as heat energy is absorbed from the surroundings by the system. Conversely, the temperature of the system increases as it absorbs energy from the surroundings. 2. Is photosynthesis an endothermic or exothermic reaction? Why? It is an endothermic reaction because it involves a conversion of carbon dioxide and water into glucose and oxygen using energy from the sunlight. 3. We have two identical beakers labeled 1 and 2. The reaction 1 happening in beaker 1 makes the beaker warm. The reaction 2 happening in beaker 2 makes the beaker cold. Which reaction is exothermic and which is endothermic? Reaction 1 is exothermic because it releases heat energy into the surroundings, while reaction 2 is endothermic since the system is absorbing heat energy from the surroundings. 4. Answer these questions based on this energy diagram. A. The potential energy of the reactants is equal to 20 kilojoules. Potential energy of the products, it's 50 kilojoules. Activation energy for this reaction equals 100 kilojoules minus 20 kilojoules equals 80 kilojoules. The energy change or enthalpy change for the reaction equals 50 kilojoules minus 20 kilojoules, which equals plus 30 kilojoules. Since the enthalpy change is positive, this reaction must be endothermic. If we add a catalyst to this reaction, the activation energy will be lowered. How does the catalyst affect the potential energy of the reactants and the products? It does not affect the potential energy of the reactants or the products. Does the catalyst affect the enthalpy change or the energy change of the reaction? No, it does not. While a catalyst can speed up the reaction by lowering the activation energy barrier, it does not change the difference in potential energy between the products and the reactants. So the enthalpy change of the reaction remains the same whether a catalyst is present or not. 5. Use the bond energy values to determine if this reaction is exo or endo. H2 plus Cl2 gives 2HCl, and the HH bond is 436 kilojoules per mole, Cl-Cl bond is 243 kilojoules per mole, and the HCl bond is 431 kilojoules per mole. So energy absorbed to break the bonds is 436 plus 243, which equals 679 kilojoules per mole. Energy released when bonds are formed is 2 times 431, which equals 862 kilojoules per mole. So the change in energy or enthalpy change here is energy absorbed minus energy released, which equals 679 kilojoules per mole minus 862 kilojoules per mole, which equals negative 183 kilojoules per mole. Enthalpy change is negative. Energy released when bonds are formed is greater than the energy absorbed when bonds are broken. So it is an exothermic reaction. There you have it. Exothermic and endothermic processes. Please subscribe, like, and share. And I will see you next time with more science content. Happy learning. Thank you.